Okay. Yeah, sorry about the delay, guys. I ran into a tech issue with the website. It's not letting me push to the repo, so I didn't get a chance to upload the slides, but I'm gonna fix it right when I get back to my office right now after lecture. So keep keep your so yeah. So for now, let's work off the projection. And then if you have any questions, I promise the slides will be up in the next couple hours after the lecture. Okay, so last time we left off with what did we do last time? We started with linear regression. We talked about support vector machines. So the type of support vector machines we talked about, I should have clarified last time. We were specifically talking about soft margin SVMs, basically SVMs that could operate on data that isn't necessarily linearly separable. That's in contrast to hard margin SVMs, which has just a slightly different loss function, but requires separability. Okay, so that's all well and good. Then we finished the lecture with logistic regression, and so today we're going to talk a bit more about logistic regression. We're going to sort of go back over cost functions, and then we will get into multi-class classification, and then yeah, that'll be a good stop point. And then the next two lectures after this will be discussing sort of the PyTorch specific libraries and how to more effectively write the optimizers or the optimization and regression algorithms that we've been talking about for the last couple weeks. All right, so that is our plan for today. Yeah, so binary loss, binary cost functions. Let's do a brief review of what we've learned. And oops. So just a bit of data. We have a data set, and we have a bunch of labels. Okay. So with the binary case specifically, our labels are of the form 0, 1, but later in this lecture we're going to have multiple labels, basically C labels. Okay. But for now, let's consider if our labels are either positive or negative. That's the words we used last time. And it's either labeled with 0 or 1, or we could label everything with -1 and 1, right? Depends on what we're trying to do, depends on the cost functions we're trying to implement, okay? So how do we build a classifier to basically classify the data set, to be trained on the data set and classify future labels? So the first thing we discussed was linear regression. We have a linear regression model, y equals WT, the y equals some slope parameters times x. X is one or more data parameters, and we have some bias. And so we have a linear function here. We classify by assuming that there's some sort of threshold, i.e. the threshold is either 1/2, or some people just remember last time we were saying that the threshold could be 0, and we were just concerned about the sign of the y variable. Either way, whatever you want to set your threshold at is fine, because this threshold automatically gets absorbed into the bias anyway, right, as you train. So we have that linear regression model, and then what we do is we use a particular loss function, in this case the squared error loss function, named for the fact that we're taking the error, basically the difference between the predicted classification y and the actual label, and we're squaring it. Okay. So if the model, for instance, predicts a label of 1, or even like 0.8, and the actual classification is also 1, then that loss is going to be kind of small, right? It'll be very close together, which is exactly what we want. But on the other hand, if the model predicts, for instance, a 1, and the actual true label is a 0, or if it's a negative 1, either way, the loss will be big, right? So we want the loss function to reflect that when the model and the target are aligned, we want the loss function to be small. When the model and targets are not aligned, we want the loss function to be big, right? And then this will help us because then we can minimize the loss function by changing the values of W, right? That's what we want. So the least squared loss, the squared error, the squared error loss function does this well. And for simple data sets, this works very well. Now, the problem with this was, of course, that this linear model isn't really a classification model. It's just a line, right? It's just a line that gets fitted to some data. So what happens is that the data itself is not linear. The data itself has two possible values. It has some negative values and it has some positive values. So when you have a line, trying to fit basically a step function, you're not going to get an optimal fit. And specifically for values that the line is very confidently predicting positively, for instance, this large residual actually screws the model up, right? It forces the slopes to get shallower, and that's not what you want, right? Ideally, and especially in this case, we want the slope to be like this, perfectly vertical, right? We want a clear separation. But that's not what a linear model does. A linear model gets fitted to the data, all the data. So the data at the end causes a large residual, as does the data at the end causes a large residual and just messes with the fit. Okay, so linear model is good for a lot of applications, but it's also not so good for a lot of applications. And classification is one of those things it might not be so great at. So confidence is poison to linear regression. So what do we do now? We went on to the logistic function. Okay, so as we saw in the example here, there's no real reason to predict values outside of 0 and 1, or outside of -1 and 1, whichever one you're using for labels. So if we just need to predict values between 0 and 1, we should have a function that just stays within 0 and 1, right? So that's the whole point of the sigmoid function here, or the logistic function, sigmoidal, well, or whatever name you choose to use. The sigmoidal function basically states that if you have a large, what this is called, if you have a large z, z in this case is also what's referred to as a logit, just a logical bit. That's where that word comes from. If z is very large, then it means this value will be small. Yeah. If z is very large, then it means this value will be very small, and then sigma will equal 1, right? Which makes sense. If z is very small, closer to 0, it means that this value will get very large, and then sigma will be closer to 0. Okay? So that's the idea behind the sigma function, that you have basically a step. Can I make this bigger? No, whatever. Okay. So that's the idea. Oh, no, this is the loss function. Sorry. That's the idea behind, so I didn't plot the sigma function, but you guys know how it looks like. That's the idea behind the sigma function, that basically you have a step that goes from 0 when the parameter, or i.e. logit, is small, and then it goes to 1 when the logit is large, right? So you have a nice little step function there. The actual logit itself is a linear function, okay? And then, of course, we have this y, which is equal to the sigma of z, and this y will give us the actual classification. Okay? And the classification is between 0 and 1, so we don't need to have any thresholds or anything like that there. Okay? So, good. So that's good. So we have this nice little sigma function, and the question really is, how do we fit it? How do we alter it? How do we get it to fit the data? So we didn't go over this last time, but for the sake of completeness, I wanted to emphasize why we didn't do this last time, which is that really the natural thing to do in this case would be to use squared error again, right? Why shouldn't we use squared error? Last time we did, well, we did cross entropy, although I didn't call it by that name. I will in a second. But let's take a step back from what we did last time and say, why don't we just use the squared error function like last time? Basically, y is equal to, or y, which is the sigma function, is y, the error is equal to the sigma function minus the target. So the target could be 1, the target could be 0, whatever. But why don't we just use that as the squared error? So let's actually plot this loss function. So if we plot this loss function, let's assume that the target is 1. Yes, okay, good. I want to get those equations there. Okay, let's assume that this target is 1. Let's assume the target is 1. The target classification is 1. And plot the loss function. So what is this loss function doing? Basically, we have if, let me rephrase this. If z is very small, close, like a very small negative, then what does that mean? It means sigma is going to be close to 0. And then the target is 1. So sigma, the target is 1. So the total loss will be on the order of 1 squared times 0.5, which is around 0.5. Okay? Then as sigma gets larger, basically goes from 0 to 1, this error gets smaller. This is 1. This goes from 0 to 1. So as sigma gets larger, this error becomes smaller. So you go from 0.5 down to 0 for the loss. Okay? So when that logit is very large, sigma z becomes 1, and then 1 minus 1 is no error, so you go down to 0. Okay? So you have a nice little reverse sigma function for the error. Okay? So on this face, this doesn't seem like a bad thing. This does not seem like a bad thing. Basically, that you have a nice large, you have a nice continuous function. It is differentiable, so that's good there. So we could do the squared error loss. There's nothing theoretically stopping you from doing the squared error loss. There is a practical issue. Could anyone see the practical issue? Yeah, please.
If the model gets stuck on one of the flats, because the gradient is very small, it's going to take very small steps and get stuck there for a while.
Yeah, that's exactly correct. Basically, let's say that the misclassification is huge, right? Let's say that the target is 1, but for whatever reason, we initialize this randomly. Let's say we initialize this randomly to a point where the logit for this value of x comes out to like negative 10 or something. Negative 10, negative 100, right? Something very negative. So what happens? We have the loss square, and we're somewhere around here for the least squared. Okay? Okay, that's okay. We have a loss that's non-optimal, which is okay. But what's not okay is that now what do we do when we want to train a model? We take the gradients and adjust the weights based off the gradient, right? But the issue is here is that the gradient is nearly 0 here, right? So if you're super confidently wrong, if the model is super confident, but it's also wrong, then that means it will dig in further. It's like a real-life version of politics. So that's not good. It would be very hard to overcome this. And so this isn't impossible to overcome, right? I don't want to make it seem like you absolutely can never solve this issue, right? But it's going to be a tough one, okay? You would have to basically play around with some very advanced dynamic step size algorithms, right? You could possibly make this work if you use a lot of very advanced step size algorithms or optimization algorithms. But really, what's the point? What's the point of that? If you're going through hell just to make this work, well, maybe the loss function you're using isn't great, right? At a certain point, you have to look and be like, if I have to go through and use unbelievably complex optimizer to optimize this loss function, maybe the issue is the loss function, right? So this, by the way, there's a term for this. The term for this is that the loss function or the learning algorithm does not have a strong gradient signal. Basically, that's if you are confidently wrong, that if you are very wrong, that the gradient is not very responsive to your error. So what did we do? So what should we do in this case? Well, in this case, what we should do is go to a different loss function, okay? So we did something different, okay? So we did what I'm now telling you is known as cross-entropy loss, okay? Basically, we know y could be between 0 and 1, okay? And so because y is between 0 and 1, the big leap in assumption, okay? There's no real mathematical, empirical proof for why this is correct or anything like that. But because we have sort of a distribution that goes from 0 to 1, I mean, that's pretty much looks like a cumulative distribution function. So why don't we just call it a probability, right? So we could estimate that estimate this as a probability distribution that a particular target is equal to 1 or a particular target is equal to 0. Okay? So what we do in this case is look at if the target is equal to 1, right? The probability that the target is equal to 1 is equal to y. But also, we take the log of y, because the log of y, as we saw last time, it makes the math just work out better. Okay? It makes the math work out better when you have a bunch of different data points that you want to compare. Okay? This doesn't change anything. Minimizing y versus minimizing log of y should give you the same parameters for w either way. Okay? So if the target is equal to 1, then we simply say that the probability that the target is equal to 1, the probability is basically just equal to y, or log of y in this case. Okay? So if this logit is very large, again, if this logit is very large, if z is very large, this term goes to 0 and this term goes to 1, right? So if the model is very confident, so if the model predicts a large z, then it's basically saying I'm very confident that this data label has a target equal to 1, okay? Which is what we want, right? We want the model to correspond to, we want the probability to correspond to the model being correct, right? We don't want the probability to correspond to the data point being 1 or 0. We want the probability to correspond to the data points being correct, to the model being correct, Okay, so that's why we break up these two cases. This corresponds to data point is 1 or 0. We want this, however, corresponds to the data points being correct, assuming the target is equal to 1. And also, we could do the reverse. Assuming the target is equal to 0, again, we would assume if the model is correct for the target equal to 0, then we would want this value to be very small. We want that logit to be negative, ideally, largely like negative. So in that case, we take 1 minus this probability, and that corresponds to if the model, to the probability that the model is correct, assuming that the target is equal to 0. Okay? So this is what's known as the cross-entropy loss. Basically, you're taking the probabilities of the model being correct for different data labels. Okay? So we could do a whole bunch of things there. We could do a whole bunch of things from here at this point, which we did last lecture, and I don't think we need to go through it again. But the major point is that a generalized form of the cross-entropy loss is simply negative t, negative this target times log y, minus or plus negative of this target, 1 minus t, times log of 1 minus y. Okay? That's the binary cross-entropy loss, the generalized form. And you don't, this works for multiple different, like this works for all sorts of different functions, but it's most commonly seen with sigmoidal functions because sigma actually does differentiate very well. Okay. Yes, please.
Why is there no x term in the z equation there?
Why is there no?
Like the z is w transpose.
Oh, there should be a z. Oh, thank you. Yeah, there definitely should be a z. Thank you for catching that. I don't know where it disappeared to. Yeah, good. Wow, it's amazing how you could, like, your mind fills in sort of these things. Okay. So if we actually look at this loss in this case, we see something more interesting, namely that if t is equal to 1, we have two losses pretty much. We have the loss for when the true label is equal to 1, and we have the loss for when the label is equal to 0. Okay? So if the true label is equal to 1, the loss, basically, it goes very large if z is very negative. That makes sense, as we've said, or as I've said. The z being very negative corresponds to the model believing the label is negative, right? Which is bad. So we want the loss to be large. But if the logit z is very positive and the true label is 1, then the loss is going to be nearly 0, which again is what we want. The logit being very positive means that the model believes the label is positive, which it is, so we want the loss to be 0. Okay? Same thing in reverse for if the true label is 0. If the true label is 0, but the logit is very positive, this z value here is very positive, then what does that mean? It means that if this is positive, this term goes to 0, and y predicts a 1. It predicts a positive label, which is wrong, because the true label is 0. So that means the loss should be big. Then what we want, the loss gets small, only if the model predicts that the label should be negative, by basically predicting that this logit is very negative. Okay? That makes sense? So this is actually what's referred to as hinge loss. Basically, it's a hinge. Right around 0, you have a transition from a loss that goes very large to a loss that evens out towards 0. And what's nice about this hinge loss, at least the way it's done in the logistic case, is that even if you're on the correct side, let's say the true label is 1 and z is weakly positive, let's say the logic predicts a positive 1, you are correct in this case. You're absolutely correct, and the model is absolutely correct in this case. But it's not confident, and you want to punish that. You want the model to push itself to be as confident as possible. You want the model to change the data points so that for whatever data point you're working on right now, the logic gets as positive as possible because we know the true label is positive. Does that make sense? Confidence is actually incorporated into this model. Okay, so it's very similar to the support vector machine with the support vector, with the margins, right? With the margins, you had a hinge loss that basically went to 1 and then 0, right? This is almost the same thing, but it's more of a continuous function. And continuity is good for gradients. Okay? Does all that make sense? Okay. So that's binary classification. That's a rundown of what we did for binary classification. Linear regression model, least squares error, or squared error, sorry, not least squares. Linear regression, squared error, logistic regression, cross entropy loss. Okay? So that's where we're at. So we just have to extend pretty much what we've done a little bit to do multi-class regression. Okay? Why is this important? It's important because most classification problems aren't dealing with binary classifications. They're dealing with, well, multi-label classifications, more to super binary classifications. And so lots of things aren't binary, but there's still classification problems. Animal species, car manufacturers models, your final grade, all these are classification problems, but they're not binary, right? So we got to figure out a way to build models that could handle non-binary classification problems. So, more than 2 classification classes. There we go. So there are a couple ways we could go about this. We could go about this sort of the avoidance way, okay? Avoidance way says that we've already worked hard to get our linear classifiers working, and it seems like a lot of effort to rewrite a whole bunch of things. So it seems like a lot of effort to rewrite our whole our whole model just for additional data labels. So what we're just going to do is use our old binary classification to reduce, well, we're going to reduce the multi-label classification to a binary classification problem. Okay? So how do we do that? Well, we could look at a graph. Suppose we have some data points. We have some data points there. And we have multiple labels, right? We have 3 labels instead of 2. Okay? So what do we do in this case? Well, we could draw a lot of boundaries. We could, instead of having just a single binary classifier, we could have many binary classifiers. In fact, if there are C classifications, we could have C classifiers, right? And for each class, we could simply relabel the data. So to be basically, this is positive and these are negative. And then we train our classifier to simply say, this is a class triangle, this is class not triangle, right? So we could do this for we could do multiple classifiers like this. And then we're left with three classifiers, each of which considers one class to be a positive class and the other classes to be a negative class. So it'll hopefully, each of these classifiers will give you one of these lines. And then you just simply, for the final prediction, you just run the data input on every single one of these classes and find the classifier that is most confident, that this data label is positive this class. Does that make sense? So you're basically just reducing a classification problem, let's say of 3 labels, into a classification problem of, is this a circle or is this not a circle? Is this a triangle? Is this not a triangle? Is this a square? Is this not a square? And then you look at your 3 classifiers and it says, okay, triangle classifier has a output of 0.08. Square classifier has an output of 0.03. And, triangle classifier has an output of 0.8. Square classifier has an output of 0.3. And circle classifier has an output of 0.2, right? So of course, the classifier that is most confident, you just go with that and output and say that's our label. Okay. So this option actually doesn't work too badly. The code for this, for some reason, again, my computer is not acting correctly today, so the example got screwed up. So the example graph isn't rendering. But I'm going to upload it when I upload the slides later on. So this doesn't necessarily work. This doesn't necessarily not work, but it is a bit tedious. And if you have like 1,000 classes, training 1,000 different classifiers is kind of insane, right? At this point, at a certain point, the amount of work you save by not writing a new classifier code is far, far, far less than the amount of work you're putting in to generate 1,000 different classifiers, right? So it's not perfect. Okay, so this is what's known as one versus rest classification. It's not completely unknown, but it's not really common either. Okay, especially when we have sort of better classifiers available to us, which we could talk about now. So, any questions before I move on? Okay, so let's regain some footing. And so what do we know? Basically, we know that the sigmoid function, and this should have been sigma. Okay. Sigma, I don't know why. Yeah, here we go. Yeah, there we go. So we know the sigma function is defined as 1 over 1 plus e to the negative s. And so where s is just some real number, the function theta sigma s maps any real value s to a number interval 0, 1 and is monotonically increasing. So the probability gets represented by so that we saw before. And then we can also write this as some function sigma equals y times w times wtx. Okay? Okay. So, I'll fix this later. So, in the binary case, we only need one probability because p of y is equal to +1 and p of y is equal to negative, sum to 1. Okay? That's the major thing. Over here, we only needed one probability. Basically, the probability that's for a positive classification is 1 minus the probability of a negative classification. So that was good. Now the issue is we have multiple labels. We have multiple labels, but the probability that each of the labels is equal to, that y is equal to one of the particular labels, that probability should also sum to 1, right? That's the idea here, is that we had a sigmoid function, probability that the input is a positive, and the input that is a negative should be summed to 1. But if we have multiple labels, we still expect that functionality, right? We still expect the sum of all the probabilities that a input is equal to a particular label should equal 1. And the other thing we want is basically non-negativity. That basically you want this probability to exist on an interval of 0 to 1, and you don't want the probability to become negative, right? Probabilities can't be negative. Yeah, probabilities shouldn't be negative. Let's talk about that. Let's leave it at that. So, what kind of function can satisfy these constraints? Well, if a single logistic function is of the form 1 over e plus negative s, and then you could write this itself as e to the s over 1 plus e to the s, then we could add all of the different probabilities together, namely the probability that something's up here. Oh no, that's correct. Okay, yeah. Yep, there we go. So we could add these probabilities together to get a simple sum that's the sum of all the probabilities should be equal to, we should divide each of these probabilities, the probability that the particular value x, or the particular logic v, is equal to a particular label, divided by the sum of all the probabilities of all labels. Okay? So the sum of all the probabilities of all labels is basically the sum of the exponential times w times x, exponential times w, the probability of, w of the label 1 times x, the parameters associated with label 2 times x, parameters associated with label 3 times x. And then we have we have the numerator, which is simply the exponential of that linear function, the exponential of parameters associated with some label. No. The probability the probability of some label t of x is divided by the probabilities that x could be one of any possible labels. Okay? So this is basically an extension of sigmoid. Okay? And the one thing that is important to realize here is that this value can never be larger than this value, right? So it has to always be somewhere between 0. So this thing together has to always be between 0 and 1. Okay, which is good. So this function is what's known as softmax. Okay, so whereas this was a logistic function, this is a softmax function, which basically simply states that which simply tries to output something between a 0 to 1 it simply tries to output the probability that a particular data point x is equal to a label y. Okay? That's why or is equal to a particular data label t. This is what's going on. Yeah, that's why I'm stumbling. Y is equal to t. There we go. I was wondering where the arrow was. Okay. So all we want is a probability that a particular that the data point is labeled as probability t. So we simply take the exponential for that linear model for the parameters t times the input parameters x. And then we do this for all possible labels as well, for the parameters for all possible labels. Okay? So the major thing here is that, yeah, again, this right here, the very likelihood is that this cannot possibly be larger than this because this term right here is included in this summation. But there are also other terms included in this summation, namely the probability, for instance, that x is part of the label 0. That's included in the summation. Probability that x is part of label 1, included in the summation. Okay? So what this function does is basically emphasize one particular label that x, one particular label for x. And it does that because it puts this linear model inside an exponential. Okay? Because an exponential grows so rapidly, even if this wx is only a slightly larger than w0x, that slightly larger is significant when it's raised to an exponential. Right? So whatever wx, for whatever label wx is greatest, is typically going to be the highest probability among all the probabilities by a lot. Okay? So that's the beauty of softmax, is that it's basically taking a bunch of labels, it's taking a whole bunch of labels, and basically emphasizing one of the labels. It's emphasizing one of the labels, and it's emphasizing that label for which wx is greatest. And wx doesn't have to be significantly greater than, for instance, w0x. But as long as it's a little greater than w0x, then this is going to dominate all the other summations, in all the other values in that summation. So again, WTX are called logits, and every class has its own weight vector associated with it. So you are, in a way, training a bunch of different classifiers. But the beauty of doing it like this, doing this, this softmax function, is that one of these labels is going to be emphasized. And you don't have to deal with tiebreakers as much as you would with the all versus one notebook, as all versus one. One versus rest classification. Okay. So let's just train a model with the probabilistic model, and let's see if the results make sense. And so we have some example data like so. Again, we generate it the same way we did last class, except now this sample has 3 different labels, 0, 1, and 2. But the major thing is that these labels overlap. Okay? So they're not linearly separable, which kind of hampers the one versus all, one versus rest classification. There we go, one versus rest classification. So, but if you have an x equal to 0, you should probably want the highest probability to be at y equals 1. If x is at 3, we should want the highest probability to be for y equals 2. But also, we don't want the probabilities, the rest of the probabilities, to be 0 either, right? Even at this point, there's a good chance that x could be labeled as 0 or 2. We just want the highest chance to be for y equals 1. Okay? So the question is, how do we do that? And so to do that, we train our classifier. We have a maximum likelihood or negative log likelihood function. Namely, the loss is equal to the negative log times the probability. Okay? It's very similar to cross entropy, except now the probability curve is equal to the cross entropy. is equal to the softmax function. Sorry. So now that the probability is equal to the softmax function, we could plug that in. So we got this whole thing inside log, inside negative log, and we want the minimum value of that. And so what do we do in this case? We simply do out logs. For instance, the log of a minus a over b is equal to the log of a minus the log of b. We use that log identity to separate the numerator and denominator. The log of exponential times any value is simply equal to that value. That's how that comes out. And we can't do much else. We can't do much else with this summation. Okay? So we go from this negative log likelihood. We plug in the softmax, and we get a new loss function here. Okay? So this is basically saying that we want to minimize this term here. So we want the parameters times x, t, to be as large as possible because of this negative. So we want this logic to be as large as possible. That makes sense. And then we want the denominator here to be relatively small. We want the sum of this denominator to be compact. Okay? So if this is very large, the only way to decrease this denominator is to make basically everything that's not, all the classes that are not t, smaller. Right? Compress the rest of the classes, increase the value of the class that belongs to the correct label. That seems reasonable. That seems like a very reasonable thing we want our loss function to do. Okay, so how do we implement this objective function? Remember, we have a set of weights for every class. So we get a set of weights for every class. No two ways around it, right? Yeah. So we have a set of weights. We have a set of parameter weights for every class. And so we just generate our initial parameters. Remember last time we had a bias plus the actual weight plus the weight. So we had mx plus b. This includes m, and this includes b. And then we do a set of 2 for each of the different classes. So we get a matrix of 6 weights. And then we have our objective function. Namely, we have that first term. We have that first term, which is just w times x. And we have the second term, which is the log of the sum of exponential of all the logics. Okay. Nice inbuilt functions to make things easier. So we do all of this. And if we train it, we see that the loss is decreasing, which is always a good sign. That if the loss is decreasing and it's not just going crazy, that's always a good sign something is working. Now the question is, how do we visualize it? We have 6 parameters. Or, well, actually our W matrix is like so. So B times M, B times M, B times M for class 3. So the question is, how do we actually visualize this? Well, we can't plot this in parameter space anymore because there's six functions, and graphs are 2D. I mean, if it was 2 parameters, it would be much easier. But we did plenty of 2-parameter plotting. Plotting 6 parameters is going to be a really weird 3D model. So it's hard to do that. But what we could do is simply plot the probabilities, right? We have the probabilities here. We have the probabilities for each label. Okay? And so we could just simply plot it to get this, the actual probability curve for each of the labels. Okay? And so what do we see? We see that, remember the original data. When the original data, C equals 0 was a bunch of data points here. For C equals 1, there was a bunch of data points in the middle. For C equals 2, was a bunch of data points to the right. So we see that for C equals 1, if x is very small, then it's probably part of class 0. If x is very large, it's probably part of class 2. That corresponds to the data set that we synthetically generated. And also, if x is somewhere in between, if x is part of class 1, then most likely it's part of class 1. But there's also a non-zero probability that's part of class 2 and a non-zero probability that's part of class 0. Okay? Which makes sense with our intuition, which makes sense with what we saw and what we generated synthetically. Right? So that's a good way to visualize softmax, is that because I mean the number of parameters is much greater than in a binary classification, we can't really just be like, 2D plot, 2D scatter plot or anything. But we could always plot the probability distribution curves of each possible label. And so as long as it makes sense, then we're golden, right? Okay. Any questions so far? Yeah, please. Go ahead.
What's the notation where it's probability of y with the line?
What's the notation where? Oh, it's the probability of given an input parameter x. It's the probability that the label that the data point has a label y. That's what it's saying. So it's given some input. That's all that line means. Given some input x, probability that the class is the classifier that the true class belongs to some class y or t, either way. Yeah, good. Okay. So that's softmax, and that's a lot of the different model and optimizations we wanted to cover. But in anticipation for the next two lectures, I just wanted to start to sort of whet your appetite for the nice little things that PyTorch is capable of. And then next time we're going to go into a deeper dive on how the actual library is set up and how you could actually code up these classifiers. So PyTorch actually has an inbuilt function called cross entropy loss, which is, I mean, it looks very simpler to, not very simpler. It looks very simple to it's literally the cross entropy loss that we just discussed. But at least in this case, we don't have to code it out. We don't have to code it out by hand. We could simply define the logits. Why? I mean, the different logits are the parameters times x. That's good. And then we simply say the loss is equal to this cross entropy loss. And then we simply say this f is equal to the f is equal to the cross entropy loss given the inputs, given the logit inputs, and particular the ideal outputs. Okay, and then PyTorch pretty much calculates all of that itself without us having to go into it. And of course, the f.backward and optimizer step, you guys have seen that 100 times before. But you calculate the gradients, and then you modify the values. And you modify the values in this case by, instead of saying w equals required grad, well, you do put that there. You tell PyTorch to, instead of doing this W equals W minus equals alpha times W grad. You instead tell PyTorch this thing needs to be optimized, so use some gradient descent optimizer, and then at every interval do a step optimization. Okay, so this is the beauty of the torch.nn module. Okay, what we've been doing has been a very manual process, although it hasn't been that manual compared to, like, 10 years ago before PyTorch. We would have had to calculate all our gradients constantly and do everything by hand. We were getting away by not having to calculate gradients, but even the update, even the parameter update was a little manual that we've been doing so far. This little code basically says that the parameter update, we don't even need to be concerned about it because we could give the parameters to an optimizer that does a whole bunch of fancy complex optimizations to properly update the parameter. And depending on the optimizer you choose, like, it's not just a fixed parameter, fixed alpha optimizer. It has all the advanced little bells and whistles, the momentum stuff, the velocity stuff, all of that is included with most of these optimizers. Actually, the momentum is disabled here, but you could implement it if you wanted to. And yeah, and even for things like cross entropy loss, you don't have to calculate that manually. And so if you do all of this is to say, if you do all of this and go through the optimization, you still get the same values. And even things like the weights. So remember X, we had to include that extra parameter for bias, right? We had to include that different extra parameter for bias because we had to include that extra parameter, or weight shouldn't be. So we had to include that extra parameter for bias, but we don't really need to. We don't even really need to include the weights anywhere in our code. We could do a whole bunch of optimizations, and I'm going to skip ahead a bit. Yeah. We could just simply set a bias equals true. We could set the logits. We don't really have to include, the logic calculation. We could just say it's a linear layer. It's just a linear set of logits, and do a whole bunch of optimizations and gets the actual parameters, which match what we had before. Okay, so I went through that quickly on purpose. It's because we're not meant to learn torch.nn right now. This was more meant to show you where we're going to go next with the next two lectures. Namely, instead of machine learning concepts, the next two lectures are just going to be devoted to using the PyTorch library and implementing the concepts that we've learned so far in a easier for us way. And really, it's going to work better because we're using the libraries, and the libraries have been optimized by all sorts of geniuses. So things end up working better anyway. Always use libraries. That's the thing. As an algorithms professor, I could tell you, don't ever implement your own algorithms. Use a library. Anyway, that's it for today. Next time, we're going to discuss the torch.nn library. And yeah, I'll see you on Thursday.